All right. Hello, everybody. Today it's very exciting. We're going to be embarking on a guided project. So for those of you who were with us last week, you might remember that we didn't fully get through the uh, notebook going over how to use pandas and NumPy. But for what we're doing today, everything that we cover, nothing that we didn't cover last week should be super relevant or necessary. You can do it all using just what we covered last week. That being said, if any of you guys wants to have that document up, let me know and I can pull it up. But otherwise, just go ahead and open up the link for the guided project. All right. Do we all have the link open? We're all good, ready to go. No questions. All right. So for those of you who just joined us, feel free to just open up this link. We're just going to be going through our guided project today. Leave it up for a little bit longer so everyone can get on the same page. Does anyone have any questions from last week? I don't know, funny jokes, stories, complaints about a midterm that they just took at like something? Man, tough crowd. Okay. Has Jordan uploaded it yet?
It hasn't been uploaded yet. It'll be uploaded very soon.
Yeah. All right, we're all good to go. We got this link opened. Perfect. All righty. So the link you opened up to the guided project should look something like this. Hang on, let me do the lights. Got the lights. So I'm gonna zoom in. So is this big enough for everyone, or do you guys want it a little bit bigger? I can make it a little bit bigger. We're good, bigger. We're good. Okay. I'm gonna keep it like this. If at any time you can't see anything, ask me. I'm happy to read it out. I'm also happy to make the screen bigger. All right. So as we talked about last week, the first thing that we need to do with any project is import the libraries that we're using, right? So this first cell is just going to import a couple of them. We're importing, oopsie, run anyway. We're importing matplotlib.
Oh, do you want to make a copy of this first?
Oh, yeah. That's right. Also, make a copy of this so you can have it in your own drive instead of messing around on the version that's only saved locally on Chrome. All right, so we're going to be importing matplotlib. If you guys don't remember, that's basically one of the libraries we talked about. It's all about plotting our data. We didn't do too much work with it, but all of the functions that you are going to need to know, we've pretty much filled out for you. It's just to let us see our graphs and have them look nice and pretty and stuff like that. We're also importing NumPy. This one's the most important. This is what we were using for like all of last week, right? If you guys remember that. And then we're doing pandas. So we didn't have time to get to pandas last week. It's basically just a library you use for dealing with large amounts of data and messing with it. I don't believe we are going to be using it this week, and if we are, we'll let you know what you're supposed to be doing. So we're going to go ahead, import these libraries. All right, so we've imported the libraries. And so the first thing that we're going to be doing is we are going to be implementing f of x. So if you see right here, f of x should be equal to pi times x plus 10, right? Pretty simple stuff. Y equals mx plus b. You probably learned that a couple years ago. So go ahead. I'm going to give you guys a minute to take a crack at how you might go about implementing this function. And then I'm going to be looking to see if any of you guys wants to share your answer, which I'm sure you will, because you guys can all do this. I believe in you. Does anyone have any questions so far? Oh, so basically, we have our function f of x right up here, right? And that in like math, f of x would be if you took f of like 1, right? You would get pi times 1 plus 10, right? Or if,
We're just trying to code the equation that you see over there.
yeah, so we're just trying to implement this equation that you see over there. So we can do a similar, just if we do like f of 0, we get 10. And if we do f of 1, we get 10 plus pi, right? And that value will be returned. All right, have we made any progress? Any idea? Any brave soul want to share what they did? Yes. Pi asterisk x plus 10. All right. Is that all? It's okay if that's all. Okay. So first of all, you might notice this little red line underneath pi, and it's telling us pi is not defined, which is kind of a problem because we need to have pi defined. So do you guys remember, we talked about a little bit about this last week, but do you remember how we could get the value of pi? Because I will tell you, the value of pi is already being added by one of these libraries for us. NumPy does have pi. So how do we go about getting pi from the NumPy library? np.pi. Perfect. np.pi. So now, oh, look at that. Looky here. No more red line. We can see the approximation is 3.14159.265, you know, whatever, pi. Now there's one other thing that's missing from this function. And this one's a little bit trickier if you're not super familiar with Python. Return, right? Why do we need to include return? This is an open question. It can be anyone. Yes, exactly. So return is what we use to indicate what we're going to be outputting or returning after the function is called, right? Because before, when we don't have return, basically what this line of code is saying, we're going to do pi times x plus 10, and then we're going to take that number and it's just going to go away. You know, it's going to disappear when the function is not being called anymore, right? And that's not what we want to do. We want to give that number back to the user, which is why we're going to use return to return it. So this is the implementation we should be having. Next, for our input data, so we want n is equal to 100. For right now, we want to generate 100 data points. So that's why we have n is equal to 100 up here. And we want to generate 100 data points in the range of -5 to 5 inclusive, so that we can use all those different points to test f. Now, this can be done in one line using a function from NumPy we talked about from last week. Does anyone want to tell me what function they think we should be using? Yes. arange. So last week when we discussed arange, well, so for arange, the big drawback, you can make it be inclusive, but the big drawback we talked about is that when you call arange, you give it your start and then your stop and then your step, right? So it's basically like if you did 0, 1, 0.1, you would get data points spaced out between 0 and 1 with a distance of 0.1 in between, which is good for some applications, but it can be a little bit trickier if we want to just get a guaranteed number of inputs, right? There's a different function that we talked about using if we were like in a situation like this, where we had a range and we didn't necessarily know what the step should be. And instead of calculating it, we just wanted to be able to tell it, oh, I want 100 data points, or I want 50 data points. Does anyone remember what that is? Linspace, right? So a little refresher for those of you who don't remember, the linspace function is very similar to arange, but as I talked about, instead of being stop, then start, then step, it's stop, then start, and the number of data points you want in that range, right? So the way we call it linspace, because linspace is from NumPy, right? We're going to do NP, and so as we talked about last week, just a little refresher, NP dot is signifying that whatever work is coming next, if it's a variable or a function or a class, it's going to be coming from the NumPy library, right? So NP dot linspace, and then what are our inputs going to be if we want to have it go from -5 to 5 with 100 data points? What's the order of parameters? Or you can just tell me which parameter should be which. Right. -5, -5, 100. So -5 because that's where we want to start, 5 because that's where we want to end, and then 100 because that's how many data points we want. One small thing is, instead of 100, I'm going to be putting down n. The reason why we do this is because right now, yes, we want 100 data points, but what if sometime in the future we wanted like 300 data points, right? And we want to have our code set up so that our variable n is storing this value. And so later on, like let's say I write some more code, right? And it's like, for I in range 100, because I need to go over all 100 data points. This would cause some problems if I remembered, oh, I'm going to change this n to like 200, but I'm not going to change the 100 some other place. So by keeping every time we use 100 to represent 100 data points, keeping it with n, it lets us make those changes. So, all right, we're going to go ahead, generate all this input data. Now, the next step that we're going to do doesn't require any work from you. We're going to be initializing the weight and bias randomly. So what that means is that we're going to be doing, we're going to be initializing 2 random values. And so as you can see, for me, my random values were 9.2868734 and 0.0562, whatever, random numbers in between 0 and 1. And so what we're going to be doing with these is we're going to be implementing as, does it say up here? Okay. We're going to be implementing linear regression, right? Now, it's been a couple weeks since we talked about linear regression, but the basic idea is we start with some random weights for our different weights that are represented. Oh, let's see. How do I? There we go. For our different weights that are represented in our function, right? And we're trying to optimize them until we get to the point where they're pretty close to what the weight actually should be, right? Now, the reason why we initialize them randomly is just because we don't know what these values are, or I mean, we do because we're saying it's pi x plus 10, but in practice, when we're going to use this technique, we won't know what these values are, so we're just going to give them a random value. So next up, we are going to be implementing y hat. So y hat is this equation right here. If function f is the function that we're trying to learn, y hat is the function that we are modifying to learn because we're modifying what w and b are, right? So why don't we go ahead, take a second, see if we can't implement y hat. It should be pretty similar to how we're implementing f of x up here. So any questions? Have we made any progress? Does anyone think they have an answer that they're ready to share? It's totally okay if not. Yes. Yep. just like that. We're going to return w times x plus b. Up here, f of x is pi times x plus 10, which is why we did pi times x plus 10. But because we want to be able to change w and b, we're just going to do w times x plus b and not do a set value. All right. Any questions about that? Nope. All right. So actually, go. So before, when we created the array X, it was a big old honking array just like this, right? But we are going to reshape it a little bit just so we can just so that we can have NumPy use this array a little bit easier when we're writing our functions. Now, the reason why, or what's happening here, is if you guys remember the reshape command, it's basically going to take some array, some NumPy array, and reshape it to match these dimensions. So we talked a little bit about how you can sort of think of the first number as like the number of rows, and the second number is the number of columns. Before, this could be thought of as just a one-dimensional array, right? It would have just 100 different rows, and one column running all the way up and down. What we're doing here basically made it so it had one row with 100 columns. And so you can see up here, the array is just a bunch of numbers, but down here, the array contains within it one other array, which is all these 100 numbers. It's a small difference, but we do need to reshape it so we can work with it with NumPy. Any questions about that? All right, so next up, we're going to get our Y results. So basically, again, y.shape gives us 100. What this is doing is, because f of x is returning to us pi times x plus 10, and that's the function, this is essentially running the function on every single x value. And so if we go ahead and run this right here, we can see that f of, -5 is equal to, negative 5.707, right? And f of, I don't know, positive 5 is equal to 25.707, right? So any questions about that? Alrighty. So now we are going to, why hat is not fine? Oh, did I not run? So now we are going to take a look at the comparative performance of our two different functions, right? Our first function, the one that we're trying to mimic, we know the values of x and we know the value of y, right? And then our second function is represented down here with the same x values, right? Because we're going to still be plugging in those same x values, but we're seeing what y hat outputs to us. And so actually this is just going to output 0 for all of them because this is setting w and b equal to 0. But if we were to change it to w b, we could go ahead and see now we do have a little bit of a slope to it, but still it's nowhere near to the slope and the intersect that we would hope for from our trained function. Hopefully it would be pretty much an exact overlay, right? So now we're going to be moving on to our loss function, which is mean squared error. Do you guys all remember mean squared error, how it works? Is that a yes or a no? Do we want a little refresher, a little brush up, a little refresher? Okay. So mean squared error is basically a way of telling us about how much error there is overall in the entire function. And so, if you can read the math notation, you'll know what this says, but most people can't read math notation. I know it took me a really long time to learn how to, like I still forget what sigmoid means sometimes. Anyway, that's irrelevant. Basically, what this is saying is that for every single y value, we're taking the y value that we're expecting, right? And then subtracting the y value that we're predicting. So basically seeing what the difference is between of those. We're squaring it, which means that all of these are going to be positive because we don't want like, oh, if my error over here is like, +5, but my error over here is -5, our total error is 0. Like that doesn't make sense. Like, +5 and -5 should not cancel each other out. So this is making it positive. Plus, it means that the smaller errors matter much less than like the bigger errors, right? Because if you have, a difference of like 1 versus a difference of 10, like 1 is pretty close, right? So that'll be represented as just 1 because 1 squared is 1. But if you had a difference of like 10, right? 10 is pretty far away, and so it would be a difference of the error that would be given to it would be 100, right? And like, as you get smaller and smaller decimals, those are going to be smaller and smaller errors. And so we're adding up all of these errors, right? And then we're dividing by the number of elements. Because basically this is telling us, okay, on average, each one of our predicted data points is this far or has this much error to it, right? So we're now going to go about implementing mean squared error. This one's a little bit more difficult. I will tell you, so y and y hat are both going to be NumPy arrays. Y is going to have the true values, right? The yi values that we're trying to get. And then y hat is going to be a similarly shaped NumPy array of all of the values that we're predicting, right? So keeping that in mind, how would we go about implementing this? There's a couple different ways we can do it, but they all involve some measure of NumPy functions. So actually, what do you guys think the first step for mean squared error would be? Yes. Yes, right? Probably the first thing we want to do is actually figure out what the error is. And so if you're not used to working with NumPy, this can be a little bit tricky. But basically, with NumPy, if you have two arrays, you don't have to like go through the entire array and one by one like subtract them or something. NumPy by default will, as long as the two arrays are like the same size, right? If you subtract array 1 from array 2, it'll do that to each element one by one. And so we can do just that. So we would do y minus y hat, and that would be the array that gives us the difference between the y we want and the predicted y, right? Now, with this, what would be our next step? Square it. Sounds like a good idea to me. So you can surround this with the parentheses. And then if you're not aware, the way we do squaring in Python and other exponentials is two multiplication signs. So asterisk, asterisk 2. You can do like, 3 if you want to cube it, or 4 if you want to take it to the 4th power, or like, 0.5 if you want to take the square root. But we're just going to be squaring it. So, all right, we're getting close. What's there? Yes. MP dot what? Oh, square root?
Oh, wait, that's good.
That would take the square root. NumPy does have a function, I believe, for taking every element in an array to an exponential power, but also the makers of NumPy were very nice and they made it so most arithmetic functions with scalar values work the way you would imagine them to. So now we have our array, right? It's an array of every single difference squared. So now how could we go about figuring out the mean squared error? And there's a couple of ways of doing it. Yes. You could absolutely use the sum function. So yes, because these are, so the question was, it's just dot sum. So these are NumPy arrays, which means that they have different functions you can call on them. And so if you are, yes. So one second. So he said, can you use the mean function? And you can, but we're gonna finish our implementation using this way first, at your suggestion. But basically you can just dot sum and call this function on it, and it will return the sum of all the values. And then finally, we would need to divide it by the number of values, which how could we get? Divided by, how would we get the number of values in the array? Yes, yes. So dot shape is the right path, but we got to do a little bit more. So first of all, what would we call dot shape on? Yes, because so if we go up here, we can see when we call, or so you can see dot shape returns to us the shape, right, of the array. So we could call it on y. We could also call it on y hat, because these two arrays are supposed to be the exact same size, right? So it really doesn't matter. But what does matter is this will give us an error. And can anyone tell me why? Take a look at when we call y dot shape, what gets returned. Yes. Right. When we call dot shape, we're going to be returned some sort of like tuple like this, right? And we can't really divide by this. We got to figure out what element we need to return. So what index would the number of values in the array be at? 1, right? Because if we go up here, we can see, okay, we have 100 values in our array, right? And so the 100 value is going to be the second one here. And that's because we reshaped it up here to be of size 1/100, right? And so absolutely. So this is one way of doing it. But as our friend, what's her name? Min Young? Yeah. All right, Min Young. He said we could just use the average function, right? NumPy has a built-in average function for us. So, or actually, hang on. Just to show you guys that this works, if we run this and then the average function. So NumPy has a built-in average function, right? And if we do NumPy.average y minus y hat, squared, it'll do the exact same thing, right? Because when we average something, we add up all the elements and then we divide by the number of elements, which is the exact same thing we just did. But this is just a little bit cleaner, done with fewer steps. And so whenever NumPy has like a built-in way of doing things, it's usually what I would recommend doing, because it'll probably be a little bit faster. So any questions so far? Nope. All right. So moving on, we're going to talk a little bit about dot products. Does everyone remember what dot products are, or have some idea? Or do you want a little refresher? We can do a little refresher if that's All right, so let's do a little bit of a refresher. So this is some linear algebra, or if you've only taken like up to 32A, it'll be it'll be like the vector multiplication you learn. But basically, what's happening is we have two lists of numbers of the same length, and we're going to multiply each number that corresponds to one another. So like, if it's like 1, 2, 3 dotted with 0, 1, 2, it would be 1 times 0 plus 1 times 2 plus 2 times 3, right? So That's what the dot product is. Now, if we want to be technical about it, in linear algebra, it's where you have two one-dimensional matrices, one that is just one column, and the other is just one row that have equal lengths, and then we can do matrix multiplication on the two of them, which is gonna, I'll explain why that's relevant. But basically, if you get the basic idea, list of numbers, another list of numbers, multiply them all together and add them. That's what you need to know for right now. And so that special operation is called a dot product. And so if we go ahead, and now we see how to call the NumPy dot function. Now, what's important to note here is we are doing c dot t. Now, when you do dot t on a NumPy array, it does a transpose. So a transpose is from linear algebra. It's basically every single row is going to become a column, and every single column is going to become a row, right? So if these right now have one row and three columns, after the transpose, it'll have three columns and one row, which is important because, as I talked about, when we're doing it in linear algebra, we're doing matrix multiplication, which means that we have to have one that has that is, one row and however many columns that you want, and then another that's one column and is however many rows you want, and those two numbers have to be equal. So when we call the transpose function, it'll transform it into an array that NumPy can do the dot product on because of linear algebra rules and stuff. So if we go ahead and do like c dot t, you can see how up here, C is one array, right? Or one row, just 1, 2, 3, right? But then after we transpose it down here, it's 3 rows, right? So 3 different arrays, each with only one column in them. Does that make sense to everyone? All right, I'm gonna assume that means you understand that what the transpose does. If you haven't taken linear algebra yet, you'll learn a lot more from probably a much more eloquent professor than me. And so basically, if we go through and we do np dot dot and take the dot product, we could see that for the first one, we are getting A dotted with C transpose. So in other words, this array dotted with this array, and this is going to give us 14, right? And if we math it out, that checks out. 1 times 1 is 1, 2 times 2 is 4, 3 times 3 is 9, 9 plus 4 plus 1 is going to be 14, right? But what we see over here is that it's not the same behavior if we do the transpose of A. Now, the reason why that is because when you're doing matrix multiplication, and this is getting into linear algebra. So if you haven't had linear algebra yet, this might be a little bit confusing. Just accept what I'm saying. There's a lot more going on behind the scenes. But basically, when you have two matrices, they both have some number of rows and some number of columns. The first matrix, the number of columns has to be equal to the number of rows, right? And so once you're done multiplying it out, it'll be the number of rows from the first matrix and the number of columns from the second matrix. So when we do the transpose, A has 1 row and 3 columns, and then C transpose has 3 columns, has 3 rows and 1 column, which means that if we take the number of rows from the first one and the number of columns from the second one, we're going to get an array of size 1, 1, as in one object, okay? But if we do A transpose over here, all of a sudden, the first matrix that we're multiplying is going to have 3 rows, and then the second matrix is going to have 3 columns, so the ultimate matrix is going to end up being a 3 by 3 matrix. So, like, it's a bit confusing because it's not like normal multiplication. You can't just like switch the order of matrices. It represents some stuff with like functions and like, you don't really have to worry about it. But because the good people at NumPy acknowledge that this can be a little bit confusing sometimes, especially if you want to get the effects of a dot product without actually, having to use the dot product function, and worry about, what if I mess up? Oh, I'm going to do A transpose instead of C transpose, and all of a sudden I have, this big old 3x3 array that is going to totally mess everything up. They made it so if you do A times C, we can multiply each one of these values together, right? So it would be like 1 times 1, 2 times 2, 3 times 3, and then we can just do like dot sum and sum them all up and get, in effect, a dot product with a few extra steps. So that was a lot. Any questions at all? And don't worry if you don't understand like all the linear algebra, or if like the words I'm speaking sound like gibberish to you. It's something that you will probably learn in your time at UCLA. If not, there's tons of fantastic YouTube videos and online tutors who explain this stuff way better than I ever could. All right, so now we are going to calculate the gradient. So does everybody remember what the gradient is? It's totally okay if not. We can do a little fresher. Are we good, or we want to do a little? Absolutely. So with the gradient, we're basically saying for each variable in our function, so in our case, if we go all the way up here, for y hat, the variables in our function are w and b. It's not x because w and b are the variables that are changing value, right? Because we're changing them at each step along the way. X, we're always going to be feeding in like the same 100 points, right? So we use that, and we take the partial derivative with respect to each variable, and that's how we determine the gradient. Now, those were a lot of words, so let's break them down. The partial derivative is from multivariable calculus, and it's basically, does everyone know what a derivative is? All right, we're all good on that one. Basically, you take the derivative with respect to whatever variable, right? So if we're taking the partial derivative with respect to w, we're going to treat every other variable, so in our case, just b, but if it was like, wx plus b plus c plus z plus d, right? We would treat all of those like they were constants. So if we take the partial derivative of this with respect to w, what would we get? Just x, right? Now, if we took the partial derivative with respect to b, what would we get? 1, right? And so when we look up here, this is how you write out a partial derivative. So like the partial derivative of the loss function with respect to w. This is what this is saying. So if we break it down by chain rule, when we take the derivative with respect to w of y hat, well, y is going to be some constant number, right? Because we know it's going to be, pi times x, which we're treating like a constant for our purposes, plus 10, right? So that goes away. Or the 2 out front is because this is originally squared in mean squared error, right? And then it's not squared anymore, so we're going to move the 2 to the front, bring its power down 1. And then the derivative with respect to w of y hat, like we talked about, is just x. The derivative with respect to b of y hat is just going to be 1. So we're not going to have anything left over from that. And so we've calculated that. And what the partial derivative, or what the gradient represents, is the direction that each of those variables should go for greatest change. So what does that mean? Basically, we take the derivative and it's like, okay, if you send your w in this direction, it's going to increase by the most. And if you send your b in this direction, it's going to increase by the most. And so if you use that to represent a vector, it's like the direction, if you're doing like something in 3 dimensions, it's the direction of steepest ascent. And if you guys remember, we can reverse that the direction of steepest descent, and use that to figure out our way to some sort of local minima, hopefully. So that was a lot. Everybody, any questions at all? There's nothing wrong if there's any questions. No? All right. So we are going to work on calculating the gradients. And so we're going to be storing our gradients in a dictionary. I'm going to give you guys a minute or a couple minutes to work on this. We want gradients B to be equal to, to be equal to the NumPy array of, or we want it to be equal to this value that we can calculate, right? That's going to be the partial derivative of the loss function with respect to B. And then we want the gradient, we want the dictionary key W to correspond with the partial derivative with respect to W, both of which are represented by these two questions up here. So go ahead, give that your best shot, and let me know if there's any questions, comments, or concerns. Has anyone made any progress? Any questions? Any thoughts that you want to share with the class? Man, nothing. You guys gotta make like some progress. I'm not like I don't expect any of you to finish the entire thing, but I just wanted to know like if any of you had made anything happen so far. Any brave soul want to share what they've done so far? Mingyoung, yes. All right, come on up. Everyone give it up. Woo! All right. So what have you done so far? Treat us, give us a look.
So to add to the dictionary, you can just like square bracket the
Yes.
column name. Okay. Oh wait, sorry. I'm too used to Windows, like
No, I get it.
Microsoft one.
Whenever
Yeah.
I switch over from my Windows computer to my Mac, I always press the wrong key for a little bit. All right, beautiful, beautiful. Everyone, give it up. Woo! Great job. So, does anyone want to explain to me what all this beautiful code Minyoung wrote for us is doing? Any takers? Anyone think that they understand what's up with his code? I'll tell you, what's happening is not too dissimilar from the mean squared error function that we implemented up here. Anybody yes. All right, makes sense. Yeah, an array where every single value is the difference. Gotcha. Is X a scalar? Yes, yes, it's another NumPy array that we're using to store basically a bunch of X values that range from -5 to 5. Yes, so we're multiplying every term by their corresponding X value. Gotcha, gotcha. Perfect. Is that it? Yes, and you're multiplying it by 2. Awesome, awesome. Everyone give it up for what was your name? Nathan. Everyone give it up for Nathan. Woo! All right, beautiful. And then as I hope you can see, we're doing pretty much the same thing, just we're not multiplying it by x because for the partial derivative with respect to b, there is no x term up here, right? So any questions about the gradient function, how the math is working? I don't know, secret to my good looks, like whatever you're interested in. I'm kidding. There's no secret because there's no good looks. All right. So if we go ahead and run, I'm just gonna give you the same error. Oh, oopsie. So if we define gradients, NumPy, okay. This is the same error. That is very unfortunate. Okay. That just okay. Okay. Or no, that was a different function. Oh, okay. Okay, you know what? We're just gonna say our prayers, and that worked. And I'm not sure how that fixed it, but we're not gonna worry about it. So if we when we run our gradients function on our x, y, and our y hat values, right, we get -37 and -19, right? So again, just to repeat what I said earlier, this is telling us that this is the direction of steepest ascent for W, and this is the direction of steepest ascent for B. Or this is, or not for W or for B, but for their loss function, right? And because we're trying to minimize our loss function, right, we want it to be as close to correct as possible. If we subtract, or if we make these values negative, it'll tell us what direction to go to decrease the loss function the most, right? That's the basic intuition behind it. And so when we're training our model, we want to be changing W and B accordingly. Now, the one last little thing that we're going to talk about is these values are not necessarily great because, for example, W, we want to be pi, right? And if we're changing it by like 37, it's probably going to be pretty hard to get it really close and accurate on pi, right? So we're going to multiply it by some scalar, typically a very small scalar. We're going to refer to that as our alpha. Then we can make it so we go in smaller steps. We'll talk a little bit more about that later. So now we're going to create our entire gradient descent function. So the first thing we're going to do is we're going to get our initial predictions using W, B, and X. And a function that we defined earlier of what y is going to be. So who can tell me what function are we using to do our predicting based off of our current weights? We haven't written too many functions, so if you just guess, you have a pretty good chance. The fx function, so fx isn't a prediction, right? Fx is the value that we want. Well, so as we change our values of W and B, our prediction is going to change too, right? So what function are we using to figure out what our predictions are? Y hat, right? Because if we remember all the way up here, y hat is equal to wx plus b. We're changing W and B. So we're going to need to invoke y hat. So we're just going to do y hat W B X, right? Just like we invoked it up here. So, all right, we have our predictions. Now we have our gradients, or we want to have our gradients. We just wrote our function to get our gradients, right? So does someone want to tell me how they would call that function? Any takers? Anybody have a guess? Yes. Oh. Yes, perfect, 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 perfect. So we're just calling, just like we did up here, except we're replacing y hat with predictions because we already called y hat, right? Awesome job. What was your name? Nick. Great job, Nick. All right. Now, finally, we are going to update W and B. And so we're going to be updating it by subtracting the partial derivative for W and the partial derivative for B multiplied by some scalar that we're going to call alpha to make it so our rate of descent is different. So why don't we go ahead, try and work on this on our own. Hopefully it shouldn't take longer than a minute or two. And then we'll circle back, see what you guys have got from me. Any questions so far? Or are we doing good? All right, I'm going to take that to mean we're doing good. All right, we made any progress? Anyone got any code they want to share? Show me how they did all this. Yes, Allison, right? Yes. Makes sense to me. And then for B, right. So perfect. Just as Allison said, we are going to, it's basically the exact same code for each of these, except where we want the gradient for W and we want the gradient for B to correspond with W and B. So this should hopefully be a pretty good gradient descent function.
But it's one.
Oh, yes. Oh, yes. Why are we, are B and W are just values, right? There's some sort of, oh, okay. Yeah. Yeah, okay. There's one last little thing to do, which I forgot to mention. So when we created W and B, we called MP random.rand1. Now, when we called MP random.rand1, so see how when I call np random.rand2, it makes an array with 2 values as opposed to 1. So what that means is that when we called np random.rand1 all the way back up there, it didn't just give us a random number, it gave us an array with only 1 element in it, right? So if we want to be able to interact with it, we can't just say we shouldn't just say W is equal to W minus, because it'll be like, what, like you're doing this to an array. We want to follow much better practice, which is to, properly subscript and just say, hey, even though this is an array with only 1 item in it, we still got to tell you, I want the first item as in the item at index 0. You can also make this a little bit more concise by using the built-in minus equals. For those of you who are unaware, if you do minus equals in most programming languages, it will take subtract whatever this value is from this value over here. So it just saves you a little bit of room. So now we gotta run linear regression using the gradient descent function, setting the learning rate to 0.03. So we want to make sure that we're saving our WB and loss values. So I'll give you guys a little hint. We're going to be returning them, WB and loss, right down here. So we just got to make sure that we're calling our gradient descent function properly. So how would we go about invoking this properly, keeping in mind learning rate at 0.03? Anyone know? Any takers? So we just wrote this gradient descent function and accepts these. Yes, Mingyang. Yes. And then what was the last one? 0.03. Perfect, right? Because we're going to pass in the X, Y, W, and B values. And then finally, our learning rate should be 0.03. So if we run it, we can see that's pretty dang close to the values that we're shooting for, right? We want our weight to be pi, right? And you can see we got pretty close to pi. Hopefully your code got pretty close to pi. And then B got pretty close to 10, 9.54924. So, it was able to get mighty close to the real answer. So any questions about that? So, all right, well, and then if we go ahead and just plot the two of these lines, we can see before, before our lines were nowhere near, right? They were nowhere near close to each other, but now they seem pretty good to me. They seem just about overlaid on one another. And if we plot the loss, we can see that it started off, it had a huge loss, right? It was like its predictions were getting way off. It was nowhere close. And then boop, 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 as we get smaller and smaller, it starts off, it's dramatically decreasing the loss, and then towards the end, the loss is decreasing less and less and less. So that is how we implement gradient descent for linear regression. Any questions for me? Comments? Nathan, you're getting an error? All right. I can come take a look at that. Claire is going to be taking over for our next part on the effect of different learning rates. Everyone give it up for Claire. Woo!
Yeah, so it's pretty cool. You guys were able to implement linear regression from scratch. So we're just gonna cover something that you may or may not have thought about before we jump into the next part. So essentially what we're going to consider is what different learning rates look like. So you might remember that in the previous part you said that we're going to set the learning rate to 0.03. And that may or may not mean something to you. But here we'll see how it may or may not matter. So right now we're setting some other learning rates. We have like 0.1 and then 0.01, so 10 times as slow. So we plot all three. You notice that the loss goes down at different rates. So obviously the large learning rate loss will go down the fastest. So that's pretty cool, right? You think, oh, gee, I can just get no loss in like 0 time. That's pretty great. But can anyone think of why you might not want such a large learning rate? Yeah, so that is a chance that happens. That when you have such a large learning rate, you're never really able to get to the minimum because you're taking too large of a step. So the trade-off with being able to resolve your loss the quickest is that your accuracy may go down. conversely, though, the smaller learning rate has its own problems, which that even though it might be more accurate, it's going to take much longer, and computation time can cost money as well. So that's why it's kind of important to figure out like a good middle ground, or figure out what you're willing to value over the other. So that's where the learning rate comes in. All right. So in the next part, we're just going to take what we just learned and we're going to apply it to a real data set. So this first box is us taking this data set from GitHub. So it's SAT versus GPA. And so now we're calling the pandas library. And so as we said before, the pandas library is a good way to handle large amounts of data. And if we run this, we can kind of have an idea of what our data include. So we have our SAT scores and GPA, and you can see some statistics about them. So our first task is we want to put each column, our SAT and our GPA, into its own NumPy array. So I'll give you guys a little bit of time to do that. Okay, I'll write the first one at least. All right, and here's the rest of it. So as you can see, we're able to call columns of a CSV by referring to them with their name. So in this case, we have SAT and GPA. And so that's how we're able to extract each individual column to put in its own array. So we'll run this real quick. And so now what we're going to do is we're just going to visualize the data that we have. So right now we're just plotting SAT against GPA, and we're going to limit our X and Y axes so that we can clearly see the data. So if you run this, you'll get some sort of scatter plot like that. So it's kind of hard to see if there is any correlation or where a correlation line might be right now. So with linear regression, hopefully we can solve that problem. So your next task is now we're going to reshape SAT and GPA like we did previously so that we can work with NumPy. All right, so has anyone done this yet or would like to share what they've got so far? Yeah, you can do that. Then you can just use then you can do the same. Huh? All right, so hopefully you have something like this. We're just going to reshape it to, remember it's just one array and then, or it's a nested array sort of, and then it's got n columns as before. So if we run this, we'll see something like that. Nope. All right, so as we did before, we're just going to make a random weights and bias. So you can use the variables W2 and B2 like we have down here. You can just call it anything. So we're just going to make some new random weights and bias. Yeah. All right, does anyone have anything so far? Yep. We can just do And then yeah. Oh, so it's basically another way, in our case, you could use the length, or you could just put it in here as well. Like, it's essentially, we just want to use the size to determine the shape of linear array, because we're just converting it. Oh, yeah. If you put 0, it doesn't work. In our case, it's just the first index, yeah, because we're already making an empty array. Yeah, or you could just straight up use the count that you see here. This is not the only right way to do it. Yeah. All right, so now we have our gradient descent function from previously. So you can use that one again on this new data set. And one thing that you want to keep in mind is what learning rate you're choosing, so that hopefully you can balance efficiency versus accuracy. By the way, guys, if you're getting a weird weights and bias for this one, sometimes it helps to just hit disconnect and delete runtime. And then you can click on this box and hit run before, and then you can run this. I'm not entirely sure why it does this, but that helps sometimes, like, clear out any like overwritten variables or something. Yeah. Learning rate? Oh, that's arbitrary, so you can just pick whatever you want. I just chose something that's pretty small, because hopefully accuracy is pretty good. All right, are we all good so far? Any more questions? All right, so if we're good, then now we can just look at what we got from the linear regression. So then we can use our same graph from before. And then this says a to do, but I'm pretty sure you can just run this. And then you see that we have a so-called line of best fit like this. So this is using the linear regression that you guys implemented from scratch not too long ago. And now we've used it on an actual data set. So if we want to take a look at our loss, you can see that it looks pretty similar from before, but it's an even steeper down curve. Does anyone have any questions so far? Or any errors that you're getting? All right, in that case, we're going to skip this next section that says running linear regression on a more complex data set. We're just going to jump to logistic regression in the interest of time. But if you guys are interested and we don't get around to this, we'll be posting the solutions after today's workshop, so you can go through it. All right, and for logistic regression, I'm handing it off to Wade. Thank you, guys. No, this is all in the same one. So if you scroll down, we're skipping the whole Boston section because we're almost out of time as is.
Yeah, we got like 4 minutes, so yeah, I'll try to make it quick. So now we're gonna do a bit of logistic regression. So we are importing matplotlib, numpy, pandas, and scikit-learn. Accuracy score, train test split. Train test, there's training data and test data. So that's what that is. Okay, we just ran that. And then this just picks a random seed. And we have our fake data generation. And it's also gonna plot the data as we see here. So if we run this, we get our fake data. So why is it so clustered? Is it meant to be clustered like that? Yeah, and as we can see, because of the way that we coded this, it's very clustered. So as you see, a lot of the data is in the bottom left, and a lot of the data of the second class is in the top right. I'm not gonna figure out what that is, but yeah, basically that's the fake data we generated. And then our shape is going to give us, yeah, so these give us the NumPy arrays for X and Y. So, and then to do is to split the training and test data with train test split. And this is a one line of code. Anyone wanna try? Does anyone have any thoughts on how to do this one? Yeah? Okay. About the variables? Yeah. Yeah. Yep. Yeah. Yeah, you basically have it. So yeah. Just in the interest of time, I'll go ahead and write it. So it's X train, X test. Wait, is it?
Yep.
Oh shoot, okay. What? I see X capitalized, but the Y not. Let's find that kind of. Write that. So yeah, this so this splits our test our training and test data. So we have X train, X test, Y train, Y test. And then so we have X and Y, and then test size is basically the percent that of our data that's test. So in this case it's 20%. And that's pretty normal, I think, for a lot of linear or logistic regression problems. And random state 35, I just picked that pretty like I just picked it. It just has to be like valid, really. Oh. Oh. That's not gonna work. Okay, let me, what the, okay. I know it's, I'm just having trouble seeing the cursor. I don't have my glasses on. Anyway.
Time to go back to light mode.
Maybe. There we go. Okay. Yeah. Okay, also, classes in Python. Are you guys familiar with classes in C++? Yes? Okay, so they work pretty similarly in Python, but there are a few differences. One notable one is this notion of self. So that's not something that's like required. You don't have that necessarily in C++, but there is a similar word in C++, which is this. If you're familiar with the this pointer, self is kind of the same thing, except like the only difference is really just like it's I'm not sure if it's actually implemented as a pointer, but we just like it basically means the current iteration of the current instance of the object. So it's basically like this rectangle has B, and then this rectangle has H, right? This rectangle's H is whatever we pass in. And we do the same thing here because it doesn't know, otherwise it doesn't know which base and which height to multiply, like in this area function. So we pass in self. Even though one thing to note is that when you actually like initialize it, you're not gonna write the word self. You only do it like in the class declaration. So if we look down here, if we look here, there's no self in this rectangle declaration. So, or there's no self. So yeah, that's one thing that's a little confusing. But if we run it, we see that the array is 15, perimeter is 16. So, which is just the definition. Yeah, so all this is basically just a series of functions and things you need to know for logistic regression. It's just like all laid out here so that you can see it. So now what we're gonna do is we're gonna create a logistic regression class. So as we see here, so the first thing we gotta do, so we have the init, which is the constructor, and so yeah, we initialize epochs, alpha, verbose, and then we also initialize the parameters. Now, the first thing to do is to initialize weights and biases according to the shapes of the input. I'll give you guys a minute to work on it. Okay, so I think was that enough time for you guys? Good. Now I know it's late, it's midterm still, but yeah. So first we do the weights. For Python, you got to remember self.weights. You can't just put in weights, unfortunately, but yeah. So self.weights. So now what we do is we do np.random.rand, and then we do x.shape the 1, and then for self.biases or self.bias, we just do np.random.rand. And why do we not need to put in?
The default might be 1, but I'll get back to you on that one.
Yeah, we're gonna get back. Okay. Oh yeah, there's stuff here that like we're not gonna get time to. So for the sigmoid function, this one's pretty like, as long as you know like the basic formula, this is like a pretty simple one, I think. So it's just return 1 divided by 1 plus exp np dot exponent, which is power e, and it's -1. Right? No, -z. Oh shoot, that's true. -z. Yeah, so we pass in z as our input.
Yeah, if you look at the function call, we take in the variable z, so that's why we.
Yeah. find it. Okay. Next thing to do is we're gonna implement our prediction. So to do that, we do what? Predictions equals empty dot dot. Oh, the dot product. Okay. Yeah, so our predictions are basically our weights are basically it's essentially a well, okay, I'm not gonna yeah, essentially it's the dot product of x and our where x is our numpy array. It's the dot product of that and our weights plus our biases. So
Yeah, remember from before how we want, the point of the weight is to determine how much each feature matters, so that's what x is, and then we just dot product, so we multiply it with the corresponding. That's all there is to it.
yeah, I know it's so easy to forget because you don't do it in C++. Like, why would you? I know it's like so easy. Okay, yeah. So as you just saw there, I forgot the self. So yeah, just always put that in there. Well, not always, but like whenever it's like the instance of an object, that's when you need to call. You need the self there. And now I'm just gonna do the rest of this because we're running low on time. So I'm gonna do the loss, the gradients, and the fit. Okay, perfect. Yeah, so that's so for the loss, that's given by log loss. Oh shoot. Okay, that's yeah, that's yeah, it's a little hard. I'm like,
There you go.
I don't want to copy all that like immediately. Okay. Yeah, so basically log loss is given by is there a negative there? Oh, negative NP dot average. Let's look at that.
We can pull the equation.
Yeah. This is a little hard, but okay. Yeah, so NP dot average y times NP dot log.
If you guys are confused about this, I believe if you scroll up, we have the equations for logistic regression right there. So right now we're just implementing it in Python.
Yeah, we're just like doing it.
There you go.
Gradient.
Do you want to scroll like a little bit down so people can see? Yeah, there you go.
Yep, sounds good.
Wait, did everyone catch that or no? The gradient? No?
All right, let me. Sorry, I forgot.
Yeah, all good.
Yeah.
Just let us know when you're done. We're just going a little fast because it's getting kind of late. We don't want to keep you here for too long.
Yeah.
Is everyone good?
I'm scrolling down just a tiny bit so you can. The gradient stuff is still right. Is right. It's right up top. But I'm just gonna write here if that's all right. So yeah. Okay, so we do predictions. So we make our predictions. And we compute loss, which is y in predictions. Now we compute gradients. And now we apply those gradients to get our new weights and biases. And alpha here is our learning rate. Okay, is there anything? Are there any questions about anything I've done on this? No? Okay. Are we a little tired? Okay, I see. Yeah, I relate to that. Yeah, so I think we're kind of done, yeah.
Yeah, so that's the bulk of it. So what we've done today is we've implemented all of the parts of logistic regression from scratch. So you'll notice that there's like a couple more boxes at the end. We won't make you sit through that today. So what will happen is after this, we'll post the solution to Discord, and then you'll be able to look at it from there. And also it'll have the solutions to the part that we skipped today, the Boston data set. So you can look at that there as well. But other than that, thank you guys so much for coming to our guided project today. I know it's hard, it's week 8, and it may or may not be raining, but you guys came anyway, so we really appreciate you. So thank you.
Thank you.